I work for the National Commission of Atomic Energy and for Instituto Balseiro in thermal scattering. So that is my first talk, what is going to be about. First of all, I would like to show you where I'm coming from because it's too far away from here. Argentina is in South America, in the southern part of South America, in what is called Patagonia. So I have been traveling for more than 20 hours to be here today. And first of all, related to Argentina, we have 6 research reactors that are working. We have the first research reactor in Latin America that is called RA1. Then we have 2 small reactors that are for academic uses. That one is in Córdoba University and the other one is in Rosario University. And then we have the RA3, that is the radioisotope producer that is located close to Buenos Aires near the airport, and that is the highest power research reactor we have. We also have a critical facility for the current reactor that is close to Bariloche, and inside the Bariloche Atomic Center, the place where I'm working, we have the RA6 reactor that is used for training the nuclear engineers, and also we have experimental facilities that are prompt gamma, BNCT, we have a diffractometer, and we also have a neutrography. Now we have under development, and we start building it, a new reactor that is called RA10, that it will be close to RA3, that it has 3 main purposes. One of the purposes is the radioisotope production, then the irradiation of silicon, and also scattering experiments. This is a view of these new reactors. Here we can see the silicon facilities, then the also irradiation test, and here we have a cold neutron source that will be providing these neutrons that we are going to use for scattering, and this information is well explained in a poster we have outside, and so then you are invited to see it. Apart from these research reactors, we also have 3 power plants that are working, and one that it's in thoughts only, but it's going to be constructed with agreement with the Chinese National Nuclear Corporation. And also, apart from the nuclear power plants at the research reactors, we have INVAP, that is a company that belongs to the Argentina government, designed together with the people of the National Commission of Atomic Energy 4 reactors that were sold around the world. These reactors are the Opal in Australia, in Egypt, in Peru, and also in Argelia. So that is our nuclear situation up to today. That is what we have. So in particular, myself, I work in the Neutron Physics Department at Centro Atómico Bariloche. This department was created by Héctor Altunes, who was working in General Atomics, and when he came back to Bariloche, he founded this department. The group was created towards a neutron source that is a LINAC, that I will be talking about it in my next talk. It was a very small group, but now we are 23 people that we are working, counting researchers, technical staff, and students. We are working on neutron physics, applications to condensed matter, material science, and nuclear engineering. Also at present, we are hard working in the development of neutron scattering instruments for this new reactor I mentioned before. That these reactors, just to remember, is similar to the Opal reactor that it was built for Australia. So this is a subgroup of this big group I mentioned before. We are 3 people. We work in the development on thermal scattering kernels or thermal scattering libraries. And Rolando Granada, who is the head of that small group, He's the one that works in theory. Ignacio Marquez, who is working in the same thing but with nuclear applications, and myself, who I have been working in cold moderators, filters, or light materials. So before starting with the thermal scattering theory, I think it's good to review some properties of the neutrons. We have to remember that neutrons can behave as particles and can behave as waves. So they are going to have properties from both, from particles and from waves. So as neutrons have no charge, they can penetrate deep in the matter, so they can avoid the Coulomb force. They can go in deep, and the interactions is between the neutron and the nucleus. Right? If the material has a magnetic moment, as the neutron also has a magnetic moment, it can also happen a magnetic scattering. Right? That is a very big advantage if you compare neutrons with X-rays or with electrons. They both have charge, so they interact with the cloud of the atom. So the interaction of neutrons is good because of the penetration. Right? So if we consider the neutron as a particle, it will have a mass, it will have a velocity, it will have a momentum. Right? We can connect these things with the energy, and we can associate that with the energy that is related to a wave. A wave has a wavelength and a wave number. If we put all these things together, we can have a neutron with a certain energy, a certain velocity, a certain momentum, a certain temperature, and a certain wavelength. Right? The important thing to remember is that the higher the energy, the lower the wavelength. Okay. Another important thing, neutrons as free particles can live less than 15 minutes. That means that when we want to use neutrons as proof particles, we need to produce them in the moment. We cannot storage neutrons. So we need nuclear reactions that can get neutrons out from the nucleus. There are two main nuclear reactions that can be used to produce neutrons. There is fission in a nuclear reactor or spallation in a spallation source. By fission, we understand that the neutron strikes on a target. That target can be uranium-235. After that collisions, two other nucleus are formed together with energy and together to more neutrons, between 2 and 3 neutrons. One of that neutrons can again collide to a new target and produce again two other nuclei, more neutrons and more energy. That is what we call the fission chain. Another option is the spallation. The spallation is produced with when a high energy protons, the energy of these protons is close to 1 GeV. One of these protons collides into a heavy metal target such as tungsten, and lots of things are produced, but in that lot of things we also have neutrons. The big difference between a neutron, a fission, and a spallation is that about 1 useful neutron is produced in one fission, and 25 neutrons are produced in a spallation, right? So we can get more neutrons from a spallation source rather than with the fission. Another difference, a nuclear reactor gives a continuous beam of neutrons, while a spallation neutron source are pulse. Another big difference, fission neutrons have to be moderated because they are born as fast neutrons. So to increase the probability of producing a new fission, we did not that fast neutrons to be moderated, to be speed down, and to get neutrons with higher probability of producing a new fission. So in a fission and in a reactor, we need to moderate the neutrons, right? But the big difference with the spallation source is that the spallation cannot be self-sustaining, right? A fission reaction, yes. So these are the biggest difference. Another thing that we have to remember, in any neutron source, spallation or fissions, neutrons are born as fast neutrons. A typical energy of a fast neutron is close to 2 or 1 MeV. Right? Thus, neutrons, if you want to use them as a particle, a proof particle, if you want to do a scattering experiments, we need a thermal neutron. So we need a moderator to reduce the energy of that neutrons, independently of the source we are using. So we let this neutron to collide with the atoms of the medium, and we reduce the velocity. When neutrons have a high energy, they lose energy in collisions. They lose energy up to what moment? Up to the moment they get the equilibrium. The equilibrium means that the neutron has the same probability of giving energy to the medium than to gaining energy from the medium. That is called equilibrium. And that equilibrium is related to the temperature of the medium, and that's why that kind of neutrons are called thermal neutrons. Right? So that equilibrium depends on the temperature of the medium. So if we want to reduce even more the energy of that neutrons, what we can do is to reduce the temperature of the moderator. So in that way, we get what is called thermal neutron. This energy is associated to a room temperature neutron, right? If we put another moderator, a cold moderator, we can get what is called a cold neutron that has a typical energy close to 1 milli-electron volt. And even more, we can reduce that energy if we put an ultra-cold moderator, and we get what is called an ultra-cold neutron. So this is a typical spectrum. Just to remember, this is a typical spectrum in a nuclear reactor. Neutrons, as I have said, are born as fast, then start losing energy. They pass through a zone that is called epithermal zone, where the spectrum is 1/V. And then they get the equilibrium, and they reach this Maxwellian shape of the spectrum. The maximum of this Maxwellian here, this is related to the temperature of the system. The real spectrum is a convolution of all that three mathematical models that were put together, right? So if we want to start with scattering theory, right? We have a beam of neutrons that collide into a sample. Most of them are going to be transmitted, right? Some of them, few of them, are going to be scattered. What we are going to study is what happens when an incident neutron scatters with a sample and go to another way, right? So we have to define the incident flux is the numbers of neutrons that are crossing per unit of area and per unit of time. This is the beam intensity. And the first definition, the double differential cross-section. The double differential cross-section is the fraction of neutrons that are scattered per second into a solid angle in a fixed direction and with finite energies between A prime and A prime plus delta A, right? This is the definition. You can find all these definitions in books. This is what I'm going to talk about is very heavy, let's say. So I'm going to show you where you are going, where are you departing, and where are you getting. In the middle, you will have to believe what is done because it's difficult, right? So this is a definition. Then this double differential cross-section can be integrated in energy, in the finite energies. So we can define the differential cross-section, that is the fraction of scattered neutrons per second into that solid angle until a fixed direction. And in the other way, in the same way, we have the double differential cross-section and we integrate it in the final energies. Instead of doing that, what we can do is we can integrate in all the possible directions instead of integrating in energy, and we get what is called the energy kernels, right? That is the same. It's the number of scattered neutrons per second and energy neutrons, and its density is always defined in this interval to the final energies, right? And finally, if we do both things, we integrate in the finals energy and also in the finals angles. What we get is the total scattering cross-section, that is the total number of scattered neutrons per second in any direction and with any energy. This cross-section, this total cross-section, is a quantum property of the nucleus. It has nothing to do with the size, with the real size of the nucleus, right? But it's called cross-section because you can compare to the definition of cross-section in classical mechanical. In classical mechanical, where the cross-section is the effective area presented by the nucleus to an incident neutron, right? This is the same concept, but the important thing is that it's not related with the size of the nucleus, right? It's a quantum mechanics magnitude, and that's why we are going to have to go in deep to quantum mechanics to analyze all the processes. So the first thing we are going to analyze if we have only one neutron and only one fixed nucleus. Right? The first thing in what we have to think, remember that we are working with thermal neutrons. Thermal neutrons have a wavelength close to 2 angstroms. And we know that if the interaction of the neutron is with the nucleus, the force that is going to appear is the nuclear force, right? And we also know that the nuclear force are short-range forces, that short range is close to 1 Fermi. 1 Fermi is 10 to the minus 15 meters. 10 to the minus 15 is 5 orders of magnitude lower than the wavelength of a thermal neutron. That means that the wavelength of the neutrons see the nucleus as a point. Yes? So when the neutron is colliding with the neutron, it's for the neutron, this is a point. That is what is called, that is scattering is a point-like, right? Also, as we are working with thermal neutrons, the energy of the neutrons, we said thermal neutrons has energies close to the milli-electron volts, 25 milli-electron volts. So the energy is too low to give energy to the system. So the scattering is going to be elastic, right? So the scattering of one neutron when with one fixed nucleus is point-like and elastic. And that is the most important thing up to the moment, right? With this idea in mind, we can understand almost everything. So when we are working in quantum mechanics, we have a quantum mechanical system. What we have to do is to solve the Schrödinger equation. And to solve the Schrödinger equation, what we need to know is which is the interaction potential that is taking place in that interaction, right? So the only thing we need to know is who or which is the potential. Yeah? So we are going to do first, only for academic purposes, this simple calculation. That is, we suppose we are not going to perform all the calculation, but if we have an incident wave function that we suppose that is a plane wave, right, that is associated to the neutron that is colliding with that scattering point, when the scattering wave is a circular wave that has this shape. In this shape, what we can see is the presence of this parameter. This parameter is called scattering length. and this scattering length is a property of the nucleus, right? If we use this parameter, if you use this information to solve the Schrödinger equation with the supposing that we are scattering with only one point, what we get, after calculating, after integrating, and after everything, is that the total scattering is written as 4 pi with the scattering length with the square of the scattering length. That means that the scattering is isotropic. Yes? This is a constant. Which are the properties of this scattering length? The scattering length is a constant that depends on the nuclide and on the spin of the neutron nucleus system. Okay? It's constant. That is really important. It's constant. It doesn't depend on the angle. It can be a complex number, and the imaginary part is related to resonances, to absorptions. It can be positive or it can be negative, depending on the potential is attractive or repulsive. And the other important thing, there is no theory that can predict the values of this constant of the scattering length. These constants are tabulated, are determined experimentally, and there is no way to find a model to adjust all the information about this scattering length. This is a good thing if you compare with X-rays. X-rays, we said before that the interaction was with the cloud of the atom. So it depends on the atomic number of the atoms, right? This thing is, this parameter, the scattering length, is analog to the form factor in X-rays. So for X-rays, the bigger the atomic number is, the bigger is the interaction. For neutrons, you don't know. You have to check in tables and to know how big is this parameter, and that will give you good information about the scattering. Yes? Is constant? Yes.
Increase energy, or if we go to below energy, so changes?
No, because if you are working with fast neutrons, all this theory is not necessary, because here we are going to take into account that the neutron is so slow that has time to see how molecules or how atoms are distributed in the sample. For fast neutrons, the interaction is totally different. This theory is only for thermal neutrons, right? So now, we had before one nucleus and one neutron. Now what we are going to have is one neutron that is scattering with a system. Yes? As I said before, we need to solve Schrödinger equation. So we have to think on states, initial states and final states. So we are going to call the initial state, of the neutron with a K, the final state with prime variables, right? The same name with a prime. The state of the scattering system with a lambda, and the final state with a lambda prime, right? So we are going to look, we know from quantum mechanics that the differential cross-sections represents the addition of all the processes, in which the state of the systems goes from lambda to lambda prime, and the state of the neutrons goes from K to K prime, right? We are changing the system, the whole system, from the initial state to the final state. Fortunately, we know that the differential cross-section is written in this way. This operator takes into account the number of transitions per second from the state, the initial state, to the final state. Right? Using the Fermi golden rule, we are able to write that operator that takes the systems to the initial state to the final stage. And independently of what is written here, the important thing is that here we have a matrix element. That matrix element, again, is connected the initial state with the final state through the interaction potential. We still don't know how it looks, that potential. We are going to see that in two slides, right? But the thing is that the only thing that is here is the potential, right? So we can write this in a simple way. Here we have the information about the neutron and about the system on both sides of this matrix element, and here we have information on the neutron, right? This is the differential cross-section. If we want to write the double differential cross-section, we need to add information about the energy. We know the energy is conserved independently of what happens in the system. We know that the energy of the system plus the energy of the neutron before the scattering has to be equal to the energy of the system after the collision plus the energy of the neutron. That is always that way. So we can write, we can take profit of this, and we can say that this differential cross-section can be with a delta function that takes this into account. We can construct the double differential cross-section. Okay? One important thing is that here we have defined this magnitude that is called, that is the difference between the initial energy state of the neutron and the final energy of the neutron. Okay? This is the energy transfer, always talking about the neutron. One important thing is that we are going to be able to split the information on the particle and the information on the target, and that's why neutrons are so good, because we can separate totally the information about the sample. So now we have to think about that potential. Okay? The potential that we are going to use is a potential. We always happens that we don't know exactly which is the potential. We need to find a model. A good model that gives good results for this kind of scattering is the Fermi pseudo-potential. This potential takes into account, depends only on the position of the nucleus and on the position of the neutron. Only depends in the difference in the relative position of the particle and each atom on the sample. Okay? With that big supposition, yes, this is for each atom in the system, we can get the total potential taking an addition of every interaction. We can write the pseudo-potential, the Fermi pseudo-potential in this way, where what we can see is that the dependence in the position is written as a delta function. It has to be with the neutron position and the position of each of the nucleus that belong to the system, right? And also, and very important, here we have the scattering lengths of each of the nucleus that are present in the system, okay? With this potential, we can go and solve Schrödinger equation. Another important thing that we have to remember that is related to quantum mechanics is that in quantum mechanics, we have magnitudes that are associated to operators that can commute or not. When that operators are not commuting, the variables are called conjugate, right? And we can go from one space to the other, we can jump from spaces of one variable to the other variable through the Fourier transformation, right? So we can write the Fermi potential as a function of a position, or using Fourier, we can transform it to this variable that is there, this is associated to the moment, to the linear moment that is similar to the transfer of energy. This is a moment transferred, always related to the neutron, okay? So in the same way, we wrote the potential in space, and we wrote the potential in the other space through Fourier. So suddenly, we solve Schrödinger equation, and we get this that is easily, see that, no? Now, it's not easy. You can try to solve it. Honestly, it's only putting the potential in Schrödinger equation and to start solving it. But if you solve that, what we get is this, this expression. In the real case, what you have to do is to take into account all the final states, keeping one of the initial states fixed. So for one initial state, you take into account all the final states, and then when you get that, for each initial state, you do an average. When you do that, what you get is this equation that is called the master formula, and is the basis of the interpretation of all neutron scattering experiments. So what we are going to do is to go inside this equation and to try to understand what is the meaning of each thing that appear inside, right? Any question up to the moment? No?
No coffee break without questions.
So one thing that we have to remember is that the scattering length is a characteristic of each nucleus, of each isotope, right? Hydrogen and deuterium have different scattering lengths. Where can I know that? I go to a table, right? Then we check that. But each isotope has a different scattering length. So we have a system. We are going to have many scattering lengths that put all together will give one average scattering length for all the system and a standard deviation, let's say, related to that mean value. Right? So here it said each scatter has its own peak, varies on nucleus to another. So here, in this expression, what we have to do is to write an average scattering length and an average B squared. Right? So with this, we are going to be able to split the scattering into two components. One that is going to call coherent scattering, and that another one that is going to be called incoherent scattering. The coherent scattering will be related to the mean value of the scattering length of the system. Incoherent scattering is going to be related to this difference that is related to the standard deviation. Right? The coherent scattering is associated to interference effects. The incoherent scattering has no interference effects. In the coherent scattering, you will have a dependence in the direction of the Q vector. The Q vector, remember, that is the difference of the initial vector of the neutron and the final. Yeah? So you are going to have dependence on that in the coherent scattering and no dependence on that in the incoherent scattering. So the coherent scattering will notice the order or the structure of the material. The incoherent scattering not. So with this split, what we can do is we can write the double differential cross sections into two components, as I said before, a coherent part and an incoherent part. We can also introduce these functions that are associated with the transformation this is in energy space. Remember that in quantum mechanics, energy and time are related through the Fourier transform. So we can define this these functions that are called scattering laws, one for the incoherent scattering and one for the coherent scattering, that they are the transform of these functions that are called intermediate scattering functions. All of these functions are relations, are almost the same. It depends on the variable, right? So these correlation functions, scattering laws, and the intermediate scattering functions contain the information on the structure in the coherent part and on the dynamics in the incoherent part of the sample, right? This information is obtained in a direct way in the measurement of the double differential cross-section, okay? So the thing is, up to the moment, we thought of any system that goes through the potentials from the initial state to the final stage. We didn't care if it was a lattice or whatever. The best thing to do is that the easy way to calculate is to suppose that we have a crystal, we have a Bragg lattice, right? In a Bragg lattice, what we are going to suppose is that we have only one atom per unit cell, that is, there is no base. So we can call the position of each atom with the L, this L vector. And then we can allow each of that atom to move around the equilibrium position. With this small perturbation to the system, we can go to the previous expressions and we can write the coherent scattering in this way. And here, important things start to appear. Writing these things, here we have U and V are operators that are related to the displacement of each atoms at time 0 and in a future time, and with the atom itself and with other atoms. We have all that kind of correlations. Right? So here in the double differential coherent scattering, what we find is that all the information here, up from here to here, is related to the sample. The information about the neutron is only here. This division is related to the neutron. The other information is about the sample. This information is also about the sample, right? This factor is the bivalent factor. Is a calculation that is related to the mean square displacement of each atom around its equilibrium position, and is associated to that displacement is related to the temperature, is strongly dependent on the temperature of the sample, and this part is related to the creation of phonons. Phonons are the way to describe the normal modes of oscillation of a system. The more normal modes of the systems are a wave behavior thing, right? So we need to invent or to create a pseudo-particle that can be the carrier of that wave. That are called the phonons. Phonons are related to the collective movements of the sample, right? Phonons are related to that collective movements, are associated to solids, but it can be used as is a Taylor expansion you can use in any system. Are associated in physics, are associated to solids, but it doesn't matter. So we have here, so we said, we have something that this depends on the sample, this depends on the neutrons, this is information about the sample also, is related to the temperature, and this is related to the collective movements of the sample, okay? In the particular case that we don't have any transfer of energy from the neutron to the sample, the scattering is going to be elastic. There will be no phonon creation, right? So this particular case of the coherent scattering, we can calculate here in the double differential expression. You can do this calculation and we get this expression. This expression is maybe familiar to you because it's the Bragg scattering that applies not only for neutrons, it applies to X-rays or to electrons. It's the same expressions. And the important thing here is to notice that there is a delta function. This delta function means that this will be non-zero only in the cases that Q, that is the vector of the neutron, that has to do with the difference, with the difference of the vectors of the neutron, are equal to one of the reciprocal lattice vectors. That is the definition of Bragg scattering. It only can be possible, it can appear if we have an ordered system with these kind of things. Then maybe you heard about, you can find short orders in liquid, you can have many things, but in the general case, the thing is that the elastic coherent double differential cross-section depends on this delta function, and also, of course, of the Debye-Waller factor, right? If you have a lattice that is not a Bragg lattice, you are going to find an extra factor here that is called the form factor that takes into account that that difference between being a Bragg lattice or not. Right? So as I said before, the mean square displacements are associated to the oscillation modes. We have the number of degrees of freedoms is equal to 10 to the 23. So instead of counting each of that normal modes, what we do is we use the density of states to describe all that normal modes that are characteristic of the sample, right? So this density of states is the fraction of normal modes between this energy and energy plus a differential. And if we write these normal modes with the density of state, we can write the Debye-Waller factor in this way, right? It doesn't matter. The important thing is to remember that this Debye-Waller factor depends on that density of states. In the same way, we did that for coherent scattering. We can do the same for incoherent scattering. Incoherent, the big difference between coherent and incoherent scattering is the presence of the delta function. For incoherent scattering, we are not going to find that delta, right? It's only for coherent scattering. What we can find here is an expression that, again, depends on the Debye-Waller factors and, again, on the phonon creation. Okay, in the special case that the scattering is elastic, the expression, the previous expression, reduces a lot, and we get a dependence only on the Debye-Waller factor. What does it mean? It means that, remember that the Debye-Waller factor, we said that depends on the temperature of the system. So at low temperatures, these Debye-Waller factors goes to 1. So the lower the temperature, the scattering, if this is close to 1, this is going to be constant. So the scattering is going to be almost isotropic. Right? So the incoherent elastic scattering for low temperature samples is close to be isotropic. So I said before, phonons can be written as a Taylor expansion of this expression, right? In this expression, we are going to have order 0, order 1, 2, etc. So the first, that is one, is the elastic contribution. The second is the first, that is one phonon creation, two phonon creation, and so on. Why we write this? Because in the master formula, if we put this Taylor expansion, it is very complicated to calculate it by hand, let's say. It's almost impossible. The only case we can calculate by hand is one phonon. So here we have the expression for the coherent elastic for only one phonon, for the creation of one phonon. This is the expression. It's easy, but not that much. It can be calculated for coherent and for incoherent. Another important thing is for incoherent and inelastic of one phonon scattering, here we get the density of state. The density of state, we mentioned before that it was a characteristic of the sample. Yes? All the information of the dynamic of the system is included here. This information takes into account what does the system do when a neutron gives energy to it. Right? We are going to see that in deep. But the important thing, so it is that it is information of the dynamic of the scattering system. So what we saw that the scattering can be split into coherent and incoherent. And both of them can also be split again into elastic and inelastic. Coherence has to do with interference aspects, and incoherence has no interference. In an elastic scattering, the neutron has the same energy at the beginning of the collision and after the collision. It changed the direction, but the energy is the same. Okay? And in an inelastic scattering, the neutron can lose or can gain energy. That's the big difference. So the scattering, cross-section, the scattering cross-section can be split in four terms. Scattering coherent, coherent inelastic, coherent elastic, incoherent elastic, and incoherent inelastic, or whatever they mix. Okay? So we have four things that we can split the cross-section. Any questions up to the moment? No question? So to sum up, we have a neutron, we have the sample, we have an initial state, we have a final state. We connect the initial state with the final state through the pseudo-Fermi potential. We solve Schrödinger equation, and we can write the cross-section of the system. This only applies to thermal neutrons. I was asked there if this applies to fast neutrons. No, this is only for thermal neutrons. Why thermal neutrons? Because thermal neutrons have energies or wavelengths close to the energies of the system we are colliding with. Right? This is only for thermal neutrons. This is thermal scattering. When we have a fast neutron, the neutrons see the systems as if it were a gas. So there is another theory, and it's more easy to calculate. Okay? So the calculation, the analytical calculation of these expressions is very difficult. You cannot solve this by hand. You need a code, you need a program, or you need to approximate, right? You can calculate one phonon scattering, but not more. And normally, one phonon is not a real case. You have as much as you can. So you can use the Enjoy nuclear data processing system, that is a commercial code that is used to generate the scattering logs, the kernels, and the cross-sections for any material at any temperature. Right? This code is designed to read evaluated data in ENDF format and transform that information in the format you need for example, if you need a cross-section library for MCMP, you can use the certain module to get the format that is convenient, right? Each module of the code performs a different task and communicate with the other module. The idea of the enjoy code is to choose which are the modules you need for each calculation, right? This is the only commercial code that is exists nowadays. We have also Gasket, but it's not so used. It's not the more used in this moment. But the Enjoy is the only code that can be used. You have to pay for it. You have to have a license. You cannot download it and use it. Just use it. You need a license. But also it is the only one, but it's a little restricted because it's not useful to calculate any cross-section library to any material in any temperature. You have certain limitations, right? For example, you can calculate if you have other systems, you cannot calculate for any variable lattice, for example. You have certain fixed lattice. You also calculate under the incoherent approximation. The incoherent approximation is an approximation that gives you the calculation of the total inelastic cross-section because the coherent part is difficult to calculate. So directly it calculates the inelastic part of the scattering, the total scattering cross-section, right? In this code, you normally use alpha and beta variables that are the same variables we were using. Beta is related to the difference of the energy over K is Boltzmann constant, T is the temperature of the system. This is a dimensional variable to make calculation in an easier way. The same for alpha. Alpha is related to the transfer of momentum and again is normalized with the temperature of the system. In this way, instead of calculating the S of Q omega, we calculate the S alpha beta, that is the way that thermal scattering is known. What we need to feed the Enjoy code? Well, we need information on the system. Remember we said that with the thermal scattering theory, we were able to separate the information of the neutron and the information of the sample. Yeah? To feed the Enjoy nuclear data processing system, what we need is information on the dynamics of the sample. The dynamic is translated into this magnitude that is the frequency spectra of density of states, right? That in particular in the Enjoy code is written in this way. In the Enjoy code, you have to separate the frequency spectrum in two parts, let's say. In a continuous part where all the information related to rotations, diffusion, and all the things associated to collective movements are included in the what is called the continuous part of this. And then you have discrete oscillators for the vibrations. That are characteristics of the molecule, right? This frequency spectra can be calculated or can be generated in any way, right? One way of getting this frequency spectrum is using molecular dynamics. With molecular dynamics, you can get the full frequency spectra and you can calculate for whatever you want, right? We have many other options, but that is the most general, right? And remember, this is the way that Enjoy writes the frequency spectra. It's not the only way that it can be written. For example, So we need a cross-section library. Why we need a cross-section library? Why are we trying to put this into Enjoy? Normally, when we want to calculate, we use the MCMP code. The MCMP code comes with libraries that are useful for fast neutrons or not so thermal neutrons, let's say. The MCMP code includes the information for all the isotopes, but in what is called the free gas library. Right? We need to know details on the structure of the sample on the target, so we need to use what I call the thermal libraries. The thermal libraries are built using the Enjoy and are built putting this information into this code, right? So for example, I will show you here when the RA10 reactor project started, one of the main purposes was the silicon doping, and people who were working on that need the cross-section library of silicon, need the thermal cross-section library for silicon. So we start working on that. Fortunately, we knew that silicons that are to be irradiated in the reactor are single crystals. The good thing of single crystals is that they have only one main axis, right? So the only way where you can get a coherent scattering is if neutrons go exactly in the way of that principal axis, right? So the coherent scattering can be negligible. You can you can suppose it is not there, right? That is because it's a single crystal. If we have a polycrystal, we have a different cross-section. The cross-section we calculate is not useful, right? But for a single crystal, we can suppose that only incoherent scattering is going to take place, and we can work only on that. Enjoy is good for that, and that's what we did. What we need was to know the frequency spectrum of the silicon, the single crystal silicon. So in the first place, what we did is to start, always when we start working on a new material, what we do is we try to find in the bibliography what kind of information we have. What we found is that in this reference, we got this spectrum, right? So we put this information into Enjoy, and we got, it's not very clear, we got this thermal library. Yeah, can be seen? This thermal library, the shape of this thermal library is saying that it's inelastic. All is inelastic, right? And the cross-section library that it was included in MCMP was this one. So it's quite different. So at first, what we noticed is that we don't know if the library we built was okay or not. But what we notice is that we are going to find a difference in the calculation. Okay? So for building that library, what we did is we fed the Enjoy, and we got this one, the pink one, right? Fortunately, in that moment, we didn't, to get a single crystal silicon, it was very difficult. It was expensive, but the most difficult thing was to get a provider of that crystal. So we couldn't measure it, but fortunately, there were, in the references, we have information about a measurement that have already been done somewhere. So this is the reference where we got the experimental data. Unfortunately, what we got is this. This is the calculation, and this is the experiment, right? With that cross-section, we gave to the people that was working on that, and they made this calculation. They found that, of course, when silicon is irradiated, they need to create silicon doping consists in that you have a silicon single crystals by activation of one of the isotopes of the silicon. These silicons transmute into phosphorus, and you get the how it's called, the crystal you want, right? So what you need is to calculate how many phosphorus were created. That was done with MCMP, with the reaction rate, and the difference is here. We found that it's not the same to use the cross-section library that it was included in MCMP. We need to take into account the thermal scattering. And that is a concrete example of things that we have been doing with this. If you want more information about ENJOY, you can visit. The idea of the talk was not related to ENJOY. I think that you can visit this website. You have to pay for the code, but you can learn how to use it for free. So you can visit the page, and you can learn when it is useful or not, and which are the limitations. Also, you are going to find information about the format of the libraries, because one of the main characteristics of the ENJOY code is that you can get the library in the format you need. For MCMP, you need the ACE format. For WIMS, you need another format, and etc. You get the format you need for each application. Right? And the last thing related to this is that the pictures were taken from this book that you may know. This is a very friendly book to learn scattering. So you can download it from the web also. I have the PDF if you want. It's quite friendly to read. So I think this is the last thing. I don't know if you have any question. You should, because yes.
So how do you measure coherent and incoherent experimentally?
No, you mean about the total cross-section? The question is how to measure coherent and incoherent total cross-section? Yes, when you measure, you cannot separate. When you measure all together. You need some to put information from outside the experiment to separate the coherent, incoherent, and elastic and inelastic. For example, in the case of silicon, when you have the single crystals, you are measuring the total cross-section. But if you are measuring in a certain direction, you are getting only one of the components, because you only have coherent scattering in special cases. Right? Always what you measure is that you can measure the double differential in another kind of experiment, but the experiments we were using were total cross-section experiments. I will be talking about that in the following talk. Right?
Can this treatment describe breakages?
With the ENJOY, you mean?
Yeah.
No. You can describe the Bragg edges from some materials, because it's not, the ENJOY code is a code that it was developed in the 60s. So the calculations were slower than today, and they were only for specific cases. So you can predict Bragg edges for carbon, for example, but not for any material. I think it's in the way it is programmed. Not for silicon, for example. Yeah. Yes.
Can you treat this as alpha beta?
No, but it depends, because the S alpha beta are useful for calculations inside of a medium. It doesn't take into account the optics of the neutron. Right? For that kind of things, you use another code. You are in the middle of a neutron field, let's say. You are not following one neutron with the optics. You can use the Maxtax code for that, and it has different libraries for that. No more questions? good. So after the break, I will talk about our neutron source and on our measurements. So we can have the coffee.